Thanks, Jason, and good morning, everyone, and welcome, especially you on the West Coast with me. I hope you have your coffee with you. Just a brief background to start here. Microtrac has experience in image analysis business in both online systems and laboratory systems going back to 1989 and has been marketing a combined and integrated image analysis laser diffraction particle characterization system for over 5 years now. Some of the advantages of an integrated technology system like this include complementary particle information for validation purposes, two types of analysis, ensemble by laser diffraction and single particle counting by image analysis, multiple types of morphological information, sizes and shapes, which both contribute to how particles affect performance, and viewable particle images for quantitative verification. In this photo of Microtrac's combination image analysis laser diffraction system, the Parton size image SI unit is shown nested to the left of the blue wave laser diffraction unit. The sample dispersion controller in the lower left pumps the sample through the sample cell to the image analyzer and then upwards through the sample cell of the laser diffraction unit. So both the image analysis and the laser diffraction measurements are made on the same sample simultaneously for direct comparison purposes, and it saves manpower. Also, the system can be replumbed to only use either unit if desired, or the SI can be purchased as a separate unit only if only image analysis technology is needed. The SI can also be plumbed to measure only one pass of the sample rather than recirculating the sample. Sometimes this is a requirement imposed by the FDA on the analysis of certain pharmaceuticals. This photo diagram of the combination system shows more clearly the sample flow direction, which follows the path of the red arrows. The sample enters the left side of the SI, goes up through the sample cell of one of 3 Microtrac laser diffraction models, each with 3 non-movable lasers and 2 stationary detector arrays. The laser diffraction models, the S3500, the blue wave, and the latest model, the tri-blue, with all 3 blue lasers, are listed below with some of their major feature differences. The basic S3500 with 3 red lasers at 780 nanometer wavelength and a range of 0.02 to 2800 microns. The blue wave with 2 blue laser diodes at 405 nanometer wavelength, offering higher resolution and range at the low end, plus enhanced calculations. And the latest tri-blue model with all 3 blue laser diodes, advanced calculations which make it especially applicable for measuring nanoparticles with the greatest accuracies and resolution. This slide is an example of visual validation of the size analysis results. The volume distribution from size analysis shown in the graph indicates a multimodal distribution with 3 different modes and a small amount of fines at the low end. This is a sample of reflective glass beads used in highway coatings, with some sand added for traction. In this small excerpt from the SI's image file, we can see good round transparent glass beads, bad fused glass beads, single black opaque particles and agglomerated opaque particles, both of which are sand grains. And the small chips in 3 spots are probably abraded from the bulk sample, showing in the fine end of the size range. This is a perfect example of how visual validation can answer questions about why the size distribution is shaped the way we see it. The major mode in the distribution would be the good single beads. The next higher, the fused beads and single sand particles, and the highest, the agglomerated sand grains. This additional information from the image analyzer allows the manufacturer to add more controls to the process. A second example shown here is a sample of wollastonite crystals, a common additive to give strength to ceramic materials. The equivalent spherical diameter as volume distribution is shown at top as reported by laser diffraction. And a small segment of the Parton SI's image file is shown below, and it makes it very clear that these particles are not spherical in shape, but are long, narrow crystals. So the ceramics manufacturer can also monitor length and aspect ratio to help further characterize his additives and correlate them to final product quality, like strength in this case. The SI can be used with chemical solvents as a standard feature, as well as the laser diffraction units can. Here's a good example of how visual validation can be used to assure that the images were successfully completely obtained, even in solvents. These are adipic acid crystals, a precursor used in the manufacture of nylon, circulated here in hexane, one of the many organic solvents useful in measuring organic particles in other than water. And we'd like to thank Dr. Marty at the University of Minnesota for sharing this screenshot with us. Note here the sample addition to the sample delivery controller in the top photo. Either a dry powder or a suspension can be added to the circulating liquid chamber in the SDC. The SI sample cell, shown removed in the second photo, is the same as the diffraction cells. This design compatibility maintains as close to the same flow rates and velocities through both units as possible for consistent viewing of particles through both instruments. The Parton SI reports 27 morphological parameters. We'll take a close look at them later. The video files of each measurement are saved for later viewing and refined method development, and they can be remeasured under different settings and conditions or SOPs, standard operating procedures. All the standard data formats used in particle characterization are reported for every morphological parameter, plus up to 45 user-selectable summary data can be reported. A scatter diagram can quickly show how classifications of different components in the sample. A query window can be used to quickly evaluate different classifications for creating SOPs. And all data in the form of image file, graphs, and data tables can be readily exported to spreadsheet, copied, or printed. And finally, classifications to isolate separate sample components and filters to remove unwanted particles evaluated using the query window can be set up in SOPs. We'll touch in more detail on this and others later. This is the set of parameters Microtrac reports for its Parton SI image analyzer. Rather than go into detail in each one of these, I'll describe in 4 general terms what they measure. First, of course, is size. We give you 13 different size measurements of each particle in various diameters, lengths, widths, and more. The ratios, the last 3 columns are shapes of different natures and are generally expressed as ratios of size parameters. Form factors include a number of different parameters that indicate how closely the particle is to being a perfect sphere or various aspect ratios or elongations of the particle. Surface roughness parameters are just that. 3 different parameters can indicate the roughness factor of the particle surface. Other specialty parameters report the overall light intensity coming through the particle and the curvature of the particle as a gradient of light intensity. Just to let you relax a minute, don't be overwhelmed by the number of choices that you have here. You'll end up using very few, and they will depend on the application and specific problem that needs to be solved, and our support group at Microtrac is always there to assist. Only one size is usually chosen, along with 1 or 2 form or surface roughness parameters. These many choices exist to provide the flexibility you need to optimize your particle characterization protocol. We can remeasure any saved video file, allowing testing of different post-analysis SOP settings. This provides a very convenient method of continuous refinement of the SOP to use for the QC or process control objective that the measurement is being made for. Starting in the upper left here and then moving clockwise, select Analysis from File from the browser window, then select the video file from the sample folder desired. Then in the lab window, select Start Analysis. During the remeasurement, the images can be displayed moving through the sensing zone, or the distribution graph can be shown building. And again, the remeasurement can be made using SOPs other than used in the original analysis. The 3 windows shown above are all contained in the SI's XY display window. The XY graph in the upper left is where up to 6 different size parameter distributions can be displayed. Here we're showing the length, width, and area equivalent diameter, volume percent log distributions for a garnet sample. Any 6 of the 27 parameters can be plotted and listed in the table to the right. Also, up to 6 different historical records for one parameter can be overlaid here for comparison purposes. The windows shown under the graph is where the graph can be set up. On the left is where any of the 6 plots can be selected for setup and display. Next, the current record or a set of plots that can be selected along with any correlations, filters, or classifications, all to be discussed later. Then the distribution type can be shown, volume, count, or any shape parameter. And last, the general graph settings can be selected. In the upper right, the tabular distributions are shown, and below, up to 45 different pieces of summary data for all those 6 parameters can be selected to be displayed. This is the View Particles display window where a lot of features are available to the user for verifying the measurement by any other technology, to method development to learn more appropriate filters and classifications to apply to the sample analysis. The entire image file is viewable, sortable in any parameter, and exportable. To point out use of the many features, follow the callouts with the blue arrows clockwise, starting with selected particle. The particle in the blue box in the frame shot upper left has the values of all its parameters displayed under Data in the column in the upper right. Next, the magnification window can be used to magnify particles in the frame from 50 to 500 microns. The image file window can be raised at the Enlarge Images window line. Scale Images points to the window where different scaling of the image sizes can be chosen. The numerical data of the sort parameter can be turned on or off in the image file. Images can be sorted on any selected parameter. The scatter diagram can be selected, and a query window for use in exploring the effect of various filters and classifications can be opened. And on the top left corner of the image file, there's a tab for choosing either the images, which we're showing now, or for displaying data. When data is selected, each column of the image file will be one of the different size and shape parameters, and the rows will represent each individual image in the file. And this data file can be exported as a spreadsheet. This is the view of one expanded page of the image file. It's sorted, in this case, in descending order by length, with the length value displayed under each image. The file consists of over 11,000 images, taken in less than 2 minutes. Something that can't be done using other characterization technologies, except on very small, unrepresentative sample viewed under a microscope. Here's a classification area that has been outlined on the scatter diagram. The query window selectable in the View Particles display is a real workhorse. It's a very convenient way to evaluate and choose classifications to include in SOPs. This particle query window is selected from the Search Particles button as shown above. A group of particles can be found by defining parameter limits in this window. Here we've entered a group or classification of particles from this sample that are less than 100 microns in length and have an ellipse ratio greater than 0.85, which eliminates particles considered oversized and not very circular in shape. By clicking OK, that query window will be added to the list of queries as indicated by the arrow. Any number of queries or classifications can be created this way and selected as desired. The image file and the scatter diagram will then display and show and report data for only the classification selected. Highlighted in blue above is a classification that was already previously entered in the list of choices. It's the diameter equivalent diameter 20 microns, greater than 20 microns, and concavity less than 0.2, which eliminates particles with a diameter less than 20 microns and particles that have a very smooth surface. The percent of particles included in the classification is listed also, 98% by volume in this case. These are the first two columns of up to 7 that can be set up as classifications and filters. Here we've set up the same two we just used in the query in the View Particles display. In the first column, we have a classification which will report only particles with less than a 0.2 concavity and are greater than 20 microns in area equivalent diameter. The second classification will report only particles with an ellipse ratio greater than 0.85 and a ferrite length greater than 100 microns. In the next slide, we'll show the classification in the second column entered as a filter with the differences explained. Here we've made changes to the previous F1 classification, starting from the top down, first by making it a filter. The Boolean AND/OR operator indicates a classification and is specific in that all the parameter limits have to be met by each particle that ends up included in the classification. In other words, here they have to all be less than 0.2 in concavity, and they have to be greater than 20 microns in size. The OR operator indicates a filter and is all-inclusive in that the particles in this filter can have either an ellipse ratio greater than 0.85 or an F length greater than 100 microns. Classifications are most often used to include particles, and filters are most often used to exclude particles from the distributions reported. Below that, a name for the filter has been added. Then the mode has been changed from include to exclude. When the mode is set to include, then only the distributions of the particles defined by the classification or files are reported. When the mode is set to exclude, only the distributions of the particles not defined by the classification or filter are reported. Next, fmain is entered in the depends on window. This makes the F1 filter operate on only the results of the fmain classification, rather than on all particles. And last, below, the parameter ranges for fmain and F1 are pointed out. Any number, not only 2, of parameters can be used to define the limits on classifications or filters. Getting back to our previous glass beads application sample, this is the overall sample of a mixture of those beads. Classifications have been created defining the transparent particles, the good beads, the bad beads, and sand, and all plotted here as overlays in cum % finer by volume. 100% of the sample is shown as a red curve. The transparent particles, the green curve, make up about 70% of the total sample. The good beads, the blue curve, about 45%. The bad beads, in black, about 35%. And the sand, the violet curve, about 20% of the total sample. And all of this information is obtained from one analysis of the sample and the creation of the classifications of the different types of particles. And most analyses are performed in less than a couple of minutes.
Thank you for checking out this on-demand presentation. We hope you found the content valuable. If you are interested in learning more about our robust particle analysis capability, please feel free to send an email to jason.noga@microtrac.com to set up your complimentary sample analysis or to schedule an on-site demo. And always, to stay up to date with the latest from us, please visit microtrac.com.